Chapter 17, Dimension Reduction, Factor Models and Principal Components. Scarcity of data is not a problem in data mining applications. Usually, the opposite is true, too much data. The objective of this section is to explore ways of transforming the columns of the X matrix such that its dimension is reduced. It may be possible to construct 3 or 4 combinations of the original variables, let us call them our new factors, which then explain most of the information that is present in the matrix X. This dimension reduction step certainly makes any subsequent modeling of the response easier, as now one relates the response to a much smaller number of constructed factors. Even if there is no response to mold, it makes good sense to reduce the dimensionality of a data matrix X. Just the fact that we have data on many variables does not mean that we know what is going on. Looking at a fewer number of transformed variables may give us more useful information. We attempt to reduce the very high dimensional information down to a few important constructed factors, much fewer than P. We do this by building a simple linear model for X that represents X in a lower dimensional space. An obvious first step is to inspect all pairwise correlations among the P columns of the X matrix. A factor model is a regression on a multivariate n by P matrix X, which is X of ij, such that the mean of xij is equal to theta j1 vi1 plus theta j2 vi2, so on through theta jk vjk, where vi1 through ik are the realizations of k being less than or equal to p, which are new factors here defined for our unit I, that explain or are being shared by the data matrix of the original P variables. The coefficients, theta j1 through theta jk, are the loadings of the original variable xj, where j equals 1 through p, onto the new k factors. Principal components analysis, PCA, is a mathematical procedure that uses an orthogonal transformation to convert a set of observations of possibly and most likely correlated variables, x1 through xp, where the columns of the X matrix, into a new set of values of uncorrelated variables called the principal components. A PCA partitions the total variance in the X matrix, where V total is equal to the V of X1 through plus all through the V of XP, into variances of P newly constructed principal component scores, where the V total is equal to the V of V1 plus V of V2 through V of VP, that are now ordered from largest to smallest. The constructed variables are linear combinations of the original variables, and the weights are selected such that the linear combinations are orthogonal. The first example is European protein consumption. The data set consists of 25 units, where the European countries are n equals 25, and their protein intakes, in percentage, from 9 major food sources, where p equals 9. Here we use the data set to illustrate PCA as a dimension reduction technique. PCA finds the linear combination of the 9 variables, the columns of the X matrix, that has the largest variability and thus explains most of the variation. After finding this linear combination, the first direction, PCA looks for a second linear combination, direction, that is orthogonal to the first one and that maximizes the variance in this second direction, and so on. The hope is that one needs only a few of these linear combinations or directions to describe the data. The scores, the linear combinations applied to the original variables of the n units, are called the principal components. So we'll start with this first example. We have named it food. And now we'll check the correlation matrix of food. We strip the first column, where the country labels, from the data set. Scale equals true, so the variables are first standardized, and default is false, which is PCA food. Oh, I think I missed this. Yeah. So how many principal components do we need? We're going to plot it first. How do the PCs look? A scatter plot of the first 2 principal components with labels for country shows that Portugal and Spain are quite high in the second dimension. The loadings for the second principal component describe a diet that is high on fish, starch, or bread, and vegetables. Now we'll look at the second example, which is the monthly US unemployment rates. Here the data matrix X has n equals 50 rows, representing the 50 states, and P equals 416 columns, which are the monthly observations. Let us summarize the 416 monthly unemployment rates through a smaller set of constructed variables. We find that the first 2 or 3 principal components explain most of the variability. The first principal component represents the common trend component of the 50 time series, a time sequence plot of the average monthly unemployment rate, and a graph of the 416 loadings of the variables on the first principal component. Here, loadings are multiplied by -1, are very similar. The absolute value of the correlation between the average monthly unemployment rates and the loadings on the first principal component is 0.83. So now we'll check this. We need this for the cluster analysis. And now we can check all the states. Now we transpose so that we have 50 rows or states and 416 columns. We'll check the PCA, and now we'll plot it, where we have the unemployment of the 50 states and their variances. Now we do the first 10 values, and then we plot the negative loadings for first principal component. Next, we'll plot the monthly averages of the unemployment rates. And then below we obtain the scores of the principal components. The first 2 to 3 principal components do a good job. We could check the first 2, 3. Below we construct a scatter plot of the first 2 principal components. We assess whether an informal clustering on the first 2 principal components would have led to a similar clustering than the clustering results of the k-means clustering approach applied on all 416 components. The graph indicates that it does. The cluster assignments from k-means clustering with 3 clusters are superimposed in color on the scatter plot of the first 2 principal components. The results show that much of the k-means clustering information is already contained in the first 2 principal components.